Got it. Okay, can you see my slides?
Yes, we can.
All right, and okay, great. Let's just jump in. Should I start, or should I wait for other to join, to rejoin?
I would say you can probably start.
Okay. All right. So hi everybody. I'm Yuhai Tu from IBM Research. So I'm going to tell you a little bit about what we did in the last few years on the subject of physics for machine learning. Okay, so first of all, for those of you who know me a little bit, for the last 20 years or so, I've been working on biology, trained as a statistical physicist, so sort of biophysics is still main part of my work. So because of that, you're going to see the central dogma of machine learning. So there's three boxes, right? The DNA, the RNA, and the protein. Here's the training box. Training data is firstly, you have to feed in the training data to a model, be it LLM, MLP. At the end of the day, the model is good or bad is really determined by the test data, whether you can actually predict things right. Okay, so first arrow means that you actually find the solution. Solution means that the solution for the parameters in this model that you developed, right? So that's the learning part of optimization, usually done by optimization. Then this part is probably more interesting, or at least equally interesting, generalization, whether the model you actually come up with the parameter that you chose or you learned is actually for any good in predicting something you have not seen before. So in the over-parameterized model, like we're dealing with deep learning, usually that's not, you have many solutions, so determining generalization of a particular solution becomes very challenging and probably the most interesting problem in my mind. And people usually do going from generalization to find a good solution. How do you find a good solution is by actually adding to the optimization process, in addition to a loss function, some regularization, right? So regularization is very general. Basically find a solution with better generalization by imposing some kind of constraint that this solution needs to satisfy certain property that allows it to be good in generalization. So because of that, of course, they have two problems. To me, basically the first part, optimization, is usually done through a stochastic process. So the first thing I'm going to tell you about something that we did in the stochastic learning dynamics area. And second part is generalization. So that's topic 2. Okay, let's dive in. Before I say anything about, let me make an analogy between something that, biophysics is very well known, hard problem, right? Again, in very high dimensional space. This is a protein folding problem. I'm not talking about AlphaFold. I'm talking about real ab initio folding, right? You have an energy landscape. You want to go from some initial unfolded structure to a native structure. So the hard part of the question there is to find the solution. There's only one solution, or maybe a couple. Lowest energy, free energy. So this landscape is really rugged. You can get trapped. You can get, stay a very long time in this metastable states and so on and so forth. So, but in machine learning, I claim it's more like what people know in biology context is like a Waddington landscape. In other words, if you start with the saddle point at the top as an initial guess, you have many solutions in terms of the loss landscape that you have many equally good minima. These are not local minimum, mind you. These are all global minima, meaning that the loss, all these the blue dots are equally good. And they are equally 100% satisfy the training data, right? So which one is better? So that's the question in terms of generalization. And this is the question because this is really under constrained problem. The number of parameters is much bigger than the intrinsic degree of freedom you try to fit. Of course, in protein folding, you also have a lot of degree of freedom, the coordinates of each amino acid, but the constraint is even more, right? Constraint is that each pair, let's say, this pairwise interaction has to have a preferred distance. So it's n square constraint with n degree of freedom. So of course it's a over constraint problem. That's how it makes it hard in finding a solution. And what makes it hard in deep learning, what I think it's because it's on the constraint problem, so it's easy to find a solution, but it's hard to find which solution is more general. Okay. All right. The first part, how do you find a solution? Or what does the learning dynamics? So this is the paper we published a few years back now. So again, we really treat this as a dynamical system, right? Learning. So the point is that you start with your initial guess as a set of weights in a very high dimensional space as a point. So this is the learner particle, we call it. And as you iterate the process of, let's say, SGD, in this particular case, we studied SGD, this particle just moves, right? So eventually try to find one of these minimum. So we want to try to understand the dynamics of the motion of this learner particle in the pipe dimensional parameter space. Just treat it as a particle, right? So it turns out, okay, so it's a stochastic particle moving, stochastic process. We're just trying to understand, something maybe no machine learner or learning scientists would ever want to look into. It's kind of, they care more about the end result, but we care about the process itself. Okay. Okay, so again, treating it as a toy problem is MNIST. So people look down upon it. It's just a toy model. And we tend to like it because it's manageable. We can open up the box and look at all the weights, how it evolves and all that, right? So the horse has been beaten to death many times over. We really want to find out how it actually died, right? So how it actually find the solution and what solution is better or worse than the other. Going to SGD. So SGD, everybody knows what SGD is about. I think the historical reason for this, why people come up with SGD, is interesting to mention, because the first thing come to mind is actually, of course, GD, right? So gradient descent. So you actually can do this with a smaller data set. You actually can do that, and you can find solutions. And even for more complicated problem, you can actually do that. But the problem, I think, original motivation for people to look at the stochastic gradient descent is that the batch size, the size of the data M is huge. So to compute the gradient every step using the overall loss function is just not manageable, right? So it's too clumsy for large. So instead, every iteration, you use a loss function that's constructed based on a very small subset of data, randomly chosen subset of data, right? So you have L of mu is a subset, and the size of mu is B, right? It's the number of data points. So if you plug in the sort of continuum equation for this, you sort of get a Langevin equation. I think when I mention Langevin, that get a lot of people confused. Remember, this is not Langevin equation for Brownian motion. This is Langevin equation for SGD. In other words, the deterministic part is fine. It's gradient descent. It's just a gradient term with a learning alpha being the learning rate. But the eta, the noise, is there. All there is in SGD, right? That's different from your physical particle in the Brownian motion. And this is very important to realize. And why is that different? If you write down the equation, it's a Langevin equation, but eta is a noise by construction or by definition. Noise, the average is 0. Okay, that's fine. But this is a high dimensional vector. It's basically what is noise? Noise eta here is just alpha, the learning rate, times the gradient of the difference between L mu and the overall L, right? The delta L mu. So if you look at this noise, of course, the average is 0 over different mini batch. But the covariance of this matrix, of this noise, is actually very rich in information. It's this thing. By the way, for equilibrium system, like a heat bath, like Brownian motion, this Cij, the covariant matrix, is just the delta function, right? And it's homogeneous. It doesn't depend on theta at all, right? So that's how you can solve the Langevin equation by using Fokker-Planck equation. That's how you can get the Boltzmann distribution. That's basically here. But this SG noise is funny because it depends on where you are in your parameter space. And it's not totally, another interesting feature is that it's not isotropic, depending on which direction, actually, the noise. So it's neither homogeneous nor isotropic. So SGD learning follows, basically, in my language, when I study statistical physics, and it's a totally non-equilibrium dynamic. So any intuition you might have, you have to think it twice, whether it's actually from statistical physics, you might think twice whether you can apply it here. All right. So as I told you, we think about the learning problem as a particle moving in this potential L. We're doing downhill motion plus this noise, right? All the richness come from the noise. But still, the problem looks kind of, you know, uh, uh, scary because it's such a high-dimensional space, right? It's a very high-dimensional drift diffusion equation with this funny-looking non-homogeneous, non-anisotropic noise. So how do we deal with that? So at the end of this section, I hope I can convince you that is actually not high dimension at all. It's actually very low dimensional motion that is actually going through different dimension, of course, for any given different trial. And the funny noise actually not only funny, it's actually pretty smart. It allows you to find flatter minimum. That's basically the two takeaway point. I'll keep it in the beginning. All right. So how do we know it's low dimensions? Actually, this is not so hard. I mean, you look at the trajectory of the weights. In this case, I'm looking at the weights between two hidden layers. Each one of them have 50 nodes. So the 2,500 parameters is large, not large as billions and trillions, but it's large, right? Larger than the data set. And you look at this high-dimensional particle, and you look at the motion fluctuation, and you just look at the PCA, right? You just do PCA on it. And you figure that, okay, PCA tells you some kind of effective dimension of this motion itself. And you find that indeed, only a few modes that's important stands out. All the rest is just, very small variance. You can look at the cumulative variance. I mean, this is rank ordered, right? This component 1 to 100, the log scale. And you see up to about 40 components out of, 2,500 degree of freedom, you get 99% of the variance. So most of the motion happen in a very low dimensional space. So this is telling you something, that the dynamics itself, even though it looks kind of scary in high dimension, effective dimension is low, which is a good thing. All right. I talked about the dynamics itself, but then you can say, okay, what about the landscape, right? We talk about loss landscape. And so let's look at the landscape. Nice thing about PCA is that it gives you a coordinate system at any given point to look at I mean, this is a high dimensional loss landscape. So just plotting out the 2,500 dimension loss landscape is, again, not very informative. But let's look at the loss landscape, one-dimensional cross-section of the loss landscape along these PCA direction, right? That's what we did. The first thing we notice is that actually the loss landscape is pretty flat, all right? So this is near a solution that you find. It's not rugged, right? It's very flat. Not smooth, I should say smooth. So how flat it is that something we want to define. And once it's smooth, you can define a so-called flatness. And the way we define flatness is not by Hessian. You can do by Hessian, but that's too local to be comfortable, because sometimes locally you can have a negative value, eigenvalue for the Hessian. So what we decided to do is basically say, hey, how far do you have to go off before your loss function increase by a factor of 2, right? So this is how we define flatness. So the bigger the F, the flatter it is. Right? So the F is a flatness parameter in PCA direction I. Okay, so that you can do that for all the directions. And then you plot F of I versus I. I is rank ordered according to PCA at the variant, right? So the variance plotted below and the flatness is plotted above. These are for different choice of hyperparameter. And then you see, by and large, they actually fall on top of each other. Furthermore, you see this other trend, right? PCA, of course, is rank order, so it goes down. That's not surprising. It's by design. But you see the flatness in this corresponding direction actually goes up with I. So this is a relation that first, just sort of excited us, because this is really something very weird. You should feel very weird once you see this. Why? Because if you plot then sigma of I versus F of I by itself, take away the I, you find that the flatter it is, in the flatter direction, the fluctuation is smaller, right? It's inverse relation. To satisfy inverse variance flatness relation, go like this. This I jokingly say this is the inverse Einstein relation, because Einstein relation tells you that it should go up. When it's flatter, if it's subject to thermal fluctuation, then it should go up. And this breakdown of fluctuation dissipation theorem, and so that's good, sort of related to non-equilibrium physics, if you wish. But here's a sort of a picture, right? So the F is a flatness, so the E of X is the free energy or loss function in that direction, and X over F squared. If you look at, if the noise is indeed a thermal fluctuation that's isotropic and unhomogeneous, the strength is a constant delta, right? 2 delta. And you get very immediately that sigma square should go up when F increases. So it's just opposite. So anyway, so this immediately tells you that this is doing something very different from Brownian notion, right? So of course, you can certainly easily guess that the reason for that is that the noise is actually not so innocent. It's doesn't have not constant strength. The noise itself could be small. It has to be in the flatter direction. In other words, so then it comes to the point that what constitutes the noise, right? So here's the physical picture that keep in mind that the noise come from, so each on the left plot, the red curve is the overall loss function L, right? Each of the dotted blue line is each for a particular choice of mini batch, the loss function for that. So you can imagine basically the search process of SGD is not search down the red line. If it's a red line going downhill on the red line, that's GD, right? SGD, basically, you're moving down this landscape that constantly fluctuates.
Nice, okay.
So, is there a question? Okay, never mind. And then
Shall we go check out
the noise is really what happened here, near here, the slope, right? Remember, that's the gradient of the delta L, and the gradient of delta L here is the gradient of the overall loss function is probably 0 near here, the minimum. But certainly the variance is not, because it's just fluctuation of these. At this point, each individual loss function for individual mini batch does not have a 0 slope here. It is the variance of that gave rise to strength of the noise. And then you can imagine why along a flatter direction, that variance is also smaller, right? Because it just doesn't have for most. So anyway, by some more empirical evidence, and by some hand-waving argument about what this fluctuation of the loss function should look like, we actually can come up with the fact that it's basically the variance goes inversely dependent on the flatness, because of the noise strength actually also decreases pretty dramatically with the flatness with some power. So again, the power law, I'm not insisting on the power law itself, but the trend is definitely there across different architecture, neural network, and so on. And just going back to what I was saying before, this is, if you're going back to statistical physics, this is actually really sort of, if you look at it, what's interesting about the SGD is the noise itself. And it turns out the noise this is what I told you about, the noise, actually, the strength of the temperature, if you wish, in a particular direction, because it's anisotropic, depends on the flatness of a landscape in that direction. So it captures some information about second order information about the loss landscape. And also it goes down with time. So it's really like a annealing process, right? So if you look at the temperature defined as the variance itself at a different point and different and if you track in the particle in time, the learning particle in time, you see that actually this particular, what we call the learning temperature, learning activity, measuring the learning activity actually goes down with time. So it's really a annealing process too in time. Okay, right. So, theoretically, you can make progress by looking at a simpler structure. For example, here we looked at a two-dimensional construct of a loss landscape. That the idea is that along y equals 0 here, at the bottom, L is 0. So by this construction, y0 divided by flatness, right? F of which depends on x. In other words, x1 has flatter. It's the same minimum as x2, but it's flatter, right? Because it has a smaller curvature. So then you do analysis on this constructed loss landscape, which is probably okay. You can expand along the bottom of a valley and think that this is a good approximation. And what you find is that if you solve the Fokker-Planck equation and you have some mimics of SGD, in this case, we're just shaking this L with each SGD, each mini batch, just the shaking and maybe some, you can also put in breathing of this landscape. And you find that indeed the effective loss is the original loss plus another term, a new term that caused by, anisotropy of the loss landscape, as well as the noise strength plus the flatness, right? So the flatter it is, the lower the free energy, the effective free energy. Okay. All right. Sorry. Okay, so topic one, I quickly wrap up. So I think SGD is a very interesting thing for me to study, at least. It's a low dimension. It turns out SGD, even though it originally defined a high dimensional space, at the end of the search process, for a particular search process, it's really a low dimensional learning dynamics.
Yeah,
The relation.
I had a question. What do you
Yeah.
think sets the dimensionality of the learning dynamics?
Yeah, of course. I didn't know about this, but we have studied up. So the complexity of the data set. So it basically
Yeah,
captured. So it learned. So that's the, amazing.
That's what I thought. Yeah, I mean, for linear regression, the dimensionality, the dimensionality of the loss landscape is the Hessian of the loss landscape is the covariance of the data. So
Right.
the question is, are there nice generalizations of that statement for nonlinear networks with non-square loss functions?
Yeah, but we cannot prove it, right? So we
Yeah.
see this. We did experiment like even MNIST, you can have 2 character, 3, 4, 5, and you just see the number of the sharp directions just increases.
Uh-huh. You used like the principal components of the learning trajectory to find one-dimensional cross sections of the loss landscape. But you could also have chosen the Hessian, right? And looked at maximal eigenvalues of the Hessian, which would give you sharper directions. Are they just not aligned with the dimensions that the learning trajectory explores?
They are pretty much okay. So I didn't tell you this, but the two matrix. So I from empirically and now we have also analytically. There are two matrices. One is the covariant matrix of the noise, which I told you about.
Right.
Another thing is the Hessian, right? These are two matrices, and what we find amazingly, I act as if they're just purely
They should be related, right?
They're related. They
Yeah.
are not exactly the same as even the eigen direction, not exactly overlap, but they are highly aligned. Let's just put it this way. Not only aligned, they are aligned in such a way the largest eigenvalue for the sharper direction in Hessian H is highly aligned with the large noise direction in D in noise direction, noise covariant matrix. They're aligned, like I said. I mean, they're not totally the same. Some claim they are the same based on some mathematical construct, but those are wrong. But we can show that they're actually highly aligned. And they are not linearly aligned. There can be some exponent involved.
May I make a comment on this, please? So first of all, thanks for the talk so far. So I believe there can also be some artifacts when the time series are not long enough. Right? Clearly, the degree of alignment between the Hessian and the covariance matrix depends on the length of the time series. And
no. D can be defined every point in your space.
Pardon me?
The matrix D. I'm talking about the noise covariant matrix can be defined.
Sure, but you need some time to average over to define the covariance matrix, right? In a single time step, you have just one realization of the noise, and you can't define a covariance matrix.
No, but the noise. Remember, the noise is defined. Hold on.
I mean, we did some simulations, so we
did simulation. That's fine. Let me show you the definition.
Yes.
Yeah. This definition. You can define this. No ambiguity, every single point in your parameter space.
Sure, it's at a point in parameter space, but if you train an actual network, you have to do a time average to define it. Right? And if the averaging time isn't long enough, then there will be stronger artifacts and it will converge towards the ideal covariance matrix only in the limit of infinite averaging time.
Yeah, but maybe you're talking about the variance of the theta itself. I'm talking about the covariant matrix of the noise, which can define every point in your parameter space without any dynamics involved.
Theoretically, you can define it, but not practically at a
So
single.
I'm talking about theoretically, if you compute the D matrix constructed that way and compute the H Hessian in that position near a place where you actually have a minimum, these two matrices are aligned, highly aligned.
Yeah, but I was talking practically. If you compute it as a time average,
I don't compute in time. I only compute. I only compute the time average when I compute the. Maybe you're confused with the noise, the covariant matrix of noise and the variance of the weights. That I have to practically compute.
Yeah, and there are strong finite size effects in terms of the alignment of that, and these finite size effects can give rise to a systematic trend in the variances which one computes. So in fact, we were inspired by your work and followed up on a model, and I think we found the reason for the decrease in the variances, and that is the fact that the stochastic gradient descent noise has anti-correlations in time. And these anti-correlations
so we also find that if you read the paper, there's a mysterious correlation time, tau of I, which also seems to depend on it's anisotropic, right? So that time so if you figure out that, I'll be very happy, because that was also in the paper empirically, we see that based on the time trajectory data. But I'm talking about now is the relation that has nothing to do with time. That every single point you can try to see the relationship between, at that point, your Hessian, and that point your noise covariant matrix.
So actually, we figured these things out, and I would like to use it as an opportunity to advertise our preprint.
Absolutely.
So it's in the archive, and I can paste it in the chat.
Please send it to me. Please send it to me. Yeah. I think okay, I'm going back to this.
Can I ask a question as well?
Yeah.
So you were looking at the trajectories over some number of time steps to look at the variance and relate it to the flatness.
Right.
Over how many time steps were you looking? Were you looking over the entire training, or the end of training? Like what's?
Yeah, so the relation we showed in that paper was done after the initial transient that you actually, already come down the hill and near the basin of a solution. So it's near a solution. And the time window we did various times. I think 10 epoch is what we usually typically do.
Okay, and this was all for cross entropy loss, right?
Yeah. They're always just cross entropy loss. Yeah, we didn't do the square loss.
So one thing that you said kind of puzzled me towards the end, which is there's this result that the SGD noise covariance matrix is the Fisher information.
Yeah, that is I think that's wrong. It's based on.
Why is it wrong?
It's just that relation is okay. So there's a couple of, so the D is the covariance is Fisher, and then the Fisher is Hessian.
Fisher is Hessian near the end of training.
Yeah, end of training. But that's, I think, I forgot which part is wrong. Part of that is wrong because you, at the end, your call is just deterministic. You say, this is a 9. You don't say, hey, this is the cross entropy between whatever you get, and 90% is 9 and 10%. So you remember when you did cross entropy, if you think you actually dot into something that actually is you have to make a decision. You cannot say, hey, I think this is 90% 9 and 10% 1. That's not the right answer. So if you dot into that right answer, right, with your cross entropy, then you don't get that equality. Yeah. Anyway, okay. Yeah.
Well,
Okay, should I go on?
Okay.
I think, yeah. The second part is yeah.
Then, sorry, I think my internet froze for a second. Then there's also this phenomenon that was observed called progressive sharpening, where the top eigenvalue is actually increasing late in training until it hits this edge of stability threshold. So from that, I would have thought that the noise is actually going up late in training, which seems to be opposite to what you said, which was the temperature is sort of going down late in training.
Yeah. So when I say temperature goes down, I mean I have a global temperature with sum of all the components. That's sort of a thing. But we also look at the individual one at the end of our training. So that all depends on when do you stop, right? At least if you just use ReLU, and at the end of the training you have this very weird scaling that you can just keep going, right? And the way and then because of the cross entropy loss, you actually gain a tiny bit of loss from decrease by just scale all the way by a factor, and your loss function will actually have a gradient in that direction, and that goes on and on. And as a result, I don't know what I mean in our mind that's a trivial scale which you can kill it with some with some cutoff, which we do. But if you don't do that, I think this may not be the reason you're mentioning the phenomena that you're mentioning, but this could be. So we stop our simulation at some point.
I see.
Based on some questions. Okay, let me go on. I think I do want to get to the second part, which is kind of fun, but non-trivial. Again, it's weird, right? What is the word that you use, Surya? Unconventional. Surya wrote me an email about why I should give a talk. He said, should I quote you? My non-conventional.
Highly original and innovative.
No, you actually call it non-conventional. No, okay, so this is a weird thing, right? So, but it comes from a legitimate question is that, okay, if people say flat is better, right? Based on some argument, I think, what is this guy's name? Uber, this guy who claimed he did everything in AI, right?
Schmid-Huber.
Schmid-Huber. He actually did write a paper about flat is better. So, I mean, but the people had a lot of argument why flatter is better. So we were just trying to see, can we actually say anything more concrete as to why is flatter better, right? So here's the problem. The problem is that you have two solutions. The blue curve corresponds to the loss function in the weight space, W, and you're using the training data, right? So that's the blue curve. So they are equally good. W star are equally good in minimizing L. So why do you think they are better? One is better than the other? Well, I think again, going back to my central dogma, the test is really what you need to use, right? So assume this is highly simplified. It's not corresponds to a translation to the blue. So the green are some using the test data, but used in the weight space. Of course, the curve shifted, right? It's change. So what is better is the delta L is smaller. The solution that have smaller delta L is better. So delta L is defined as you use the weight that you discovered, W star or W star star, but instead of using test, training, you use the test, and you look at the difference. I mean, L training is going to be very, very small. The L test, how large is L test? Delta L is dominated by L test, of course. Okay, so that's what you want to decide. Of course, you can just plug in, as usual, the test data and just see numerically which one is bigger. It's not very insightful. But then we say, well, what can we do? We know a lot about the blue curve, right? We know a lot about the blue curve. So but we really want to know the green curve, the green dot, how high has to move up without changing the weight. What if we can have a corresponding point on the blue curve? So in other words, if you have the set which have the same loss, meaning that by the original way to compute delta L is to change the data from some training data to test data. what if you can do that without training the data? You're still using the the training data, but you have a different W. Of course, the W will be W star, will be shifted from the W star, the solution you'll find from the training data, by an amount delta W, which depends on the data or the difference between test and training. That's allowed, right? So still, you're not losing any information about the test, but that information is absorbed into W instead of showing up as data difference, right? So that's the idea. Well, it's easier said than done. How are you going to do that, right? So you want to find a dual weight that basically defined by this formula, right? So you changing the data is the same as without, don't change the data, but change the weight. And this delta W depends on the original weight, or W star, and the difference and the two data, right? The data training and data test data. I'm imagining you forming pairs of training and testing. It turns out it can be done. Not only can be done, it can be done many different ways. So this is the main reason is basically because if X is your input or some neuron activity at layer one with no number N1, if you have a not even fully connected, if you have a pretty densely connected network, then what you only need to do is that I have changed X to X prime, right? Xi to Xi prime. The question is, can I absorb all that change by changing W, right? But the answer is actually, it's pretty obvious because you can. You have more W than X, right? So if it's, densely connected. So you can just do that and you can figure out how to do that. And it's a linear operation. Basically, you just need the pre-activation to be the same. And not only you have one solution, you have many solutions of W prime in terms of the W. It's like this whole line will have the same loss as you change X to X prime is equal to changing W to all the points on the W on the solid line, right? So that's the duality. And of course there's a special one. We choose the special one. The special one is the one that's closest in terms of weight to the original one, right? In Euclidean measure, and you get that. And that's the duality, the minimum duality relation we use. And the delta W, you see the formula is actually pretty informative. Delta Wij is Xi times delta Xi prime. So this guy itself times delta Xi prime, the other nodes, divided by X squared. X squared is just the norm of the X, the training data. But this had to multiply by Wi prime J. So the Wi prime is here, the I prime is here to the J, right? So that's basically, so basically you can do that. And once you do that, then you say, well, okay, now I can evaluate my delta L. I make the transformation, my duality transformation. Now I only use X. So now I pair up training data and test data, pair them up, closest neighbor, whatever, right? And then I can say, okay, now I don't. So this delta LK can be evaluated by not changing X of K, but changing from W to, in this case, W to W star. And I can look at the difference between W and W star and the sort of the slope there, right? So you can do various approximations and what you thought, combining this analytical result and some empirical experiment. What we find is, of course, the delta L now this a product of two things. One is how spread out are these dual weights around the original weight, how spread out. That's sigma W of, oh, sorry. Yeah, that's sigma W of n. Another one is sigma G of n. That's how, here, if you write down the training data, it will have zero slope. But if for different pair and different shift and different pair, you'll get a different slope here, finite, but center around zero. you have a variance of that distribution, and then it comes up with this particular thing. And this is quite informative, right? So each you can decompose into different directions. Contribution is the spread of the dual weight in that direction, and how variable are the weights, are the gradient in that direction for different mini batch, or different for different mini batch. So the first thing
actually, I had a question. To get the spread of the weights in the dual directions, like, don't you need access to new test samples?
Sorry? Say
To
again.
get the spread of the weights, don't you need access to new test samples?
Yeah. So all of these have delta X in it. So I'll get to the formula. For the weight spread, it's actually very nice because I have an exact formula. And by the way,
can you predict generalization just from access to the training examples?
It comes from, so that's where I get to why flatter minimum is better. So that's,
I see. Okay.
Yeah, so there's two factors. I go with the second one, which is sigma. So this actually turned out empirically, it's very much correlated with Hessian. So this is about flatness then. So this factor says, okay, the larger it is, right? The Hessian, then sigma g will be large, sigma squared g will be larger. Therefore, if a solution that is in general sharper, that's the sum over all the different directions, then you probably are gonna have a larger delta L, therefore, less generalizable in terms of delta L, right? Another one is what Surya was asking, sigma. We know the exact formula for sigma W, right? So you can just write it down. And this goes to a very nice formula. This is basically L2 measure of the distance of the actual weight that you learned, right? Actual solution to the origin, but the metric depends on delta X, right? So it does depend on data, the difference between data. So but it's a metric that actually pretty for the data set that we tested is pretty benign. So it's just some metric, but overall, this sigma W is very much highly correlated with just the L2 norm of the W itself. As treating C, C has some structure in it. We haven't fully, explored that, but if you approximate it with, unit, matrix, it's actually pretty good approximation. And this means that smaller solution is a larger solution with larger L2 norm of the weight is actually going to give you a less generalizable solution. So this is what maybe Surya was asking. Now you can use this to say, there are two strategies for better generalization. What can we do? One is that you want to find a solution that's flatter, right? Because this reduces sigma G, right? So how do you do that? We also know from the first part of the talk that you're more likely to get to the flatter solution if you have a larger SGD noise, and you can figure out. It's easy to figure out the SGD noise strengths depend on two things: the larger learning rate and a smaller batch size give rise to a larger SGD type noise. Just the magnitude itself. The existence, it's already exists for any batch size and learning rate, but it goes, the strengths of that overall, that anisotropic noise term goes like alpha over B, roughly speaking. So we did the experiment. So basically, this is the same MNIST. We tune up of course, you can increase your learning rate, and eventually you hit the divergent, but you cannot converge. But as long as you converge, what you find is that indeed increasing SGD noise by increasing the absolute strength, what happened is that this is what we plotted sigma G, which is also basically a proxy for the Hessian, right? At the solution. And you find that the sharper solution, right, so the blue line corresponds to alpha equal to 0.001, very, very, 0.05, very, very small. As you increase learning rate, this going down, then the sharper mode, it still exists. You still have like 10 mode that's sharp, right? But the sharpness goes down. So therefore, that corresponds to the better performance in generalization. So this was shown here. And another trick everybody knows is weight decay, right? So indeed, if you put weight decay and you change beta from beta, no weight decay, beta equals 0, beta equals 0.05, 0.01, and 0.02, what do you find? If you do that, you actually don't change much for the sharpness spectrum. We call this sharpness spectrum. It doesn't change very much. However, the size of the solution, this is the measure of the size of the solution, definitely goes down. And that actually leads to the this is not a big change, but it's still a measurable change in the delta L decrease. So I think to summarize this part, I think this is the part that really convinced that the flatness is important. I know in the community, the one standard argument against flatness is the Dean et al. Paper by, I think, Bengio's group. In 2017, they said, hey, this cannot be true because, look, if you have this network, if you increase all the weight in one layer by a factor of p, decrease another layer by, divided by p, you don't change anything, right? You can see by through ReLU, this is a scale invariant based on this. You absorb all the changes, right? So therefore, if you look at the loss landscape according to W1, everything becomes sharper by a factor of p, right? But the loss function doesn't change. How do you explain that? The solution is the same? How do you explain that? Oh, this is actually trivial in our case, because when you change the flatness this trivial way, indeed you may increase the sharpness by a factor of p, or decrease the sharpness by a factor of p. You also increase the sigma w by the same factor. So it cancels out. Of course, delta doesn't change. It's the same solution. So goes the same layer, the next layer. If you look at the weights in the next layer, you find the same thing. But for physicists, this is a trivial, right? Because look, flatness is a Hessian, right? So it's a second derivative of loss with respect to w squared, right? Second derivative. The unit doesn't even match up. But on the left-hand side, you have delta L. Right-hand side, this thing called flatness. Flat compared to what, right? So flat compared to the size of the solution itself. That's the conclusion, right? So that goes into the delta sigma W. I think we use it to look at the generalization. This is a kind of important question to us. But I think this activity duality relation, I asked around, right? Including people, I was in San Diego last week. I saw Sanofsky. I said, well, Cherry, do you know anybody knows about this? I mean, either in neuroscience or in AI about the duality? He didn't, he says no. But I don't know whether you should. He has a great memory, by the way. So anyway, but I think this duality should be seriously looked at. I mean, there's a lot of things one may want to do with it. Like if you look at the sharpness direction that's in the weight space, you can probably map it back to the data space because of duality. You say, hey, the sharp direction corresponds to in probably the most serious adversarial attack, right? So, and so on and so forth. So I don't want to belabel this, but I think this is, this is again one of these unconventional things. I think people, once they looked at it, they look at the title, they don't know what I'm talking about, but it might be something interesting there. All right, to end up, I'll bring your attention to something that I think this is something that I want personally very passionate about, physics for AI, but there's another direction, right? I think those are complementary as AI for physics, that once you really understand how learning systems work in a particular system for a particular type of data, you might be able to develop better interpretable AI tool for scientific discovery. So this is sort of like the idea that went into a special feature in PNAS that Herbert Leving and I co-edited, and it was published earlier this year. And I think a number of people in the group actually contributed to this collection, which is very good. Another thing I should mention is that David Schwab and I, since 2021, since APS meeting has resumed its in-person meeting, has actually organized invited session and focus sessions on statistical physics meets machine learning, basically bring ideas from physics to try to bear on machine learning, try to understand these sort of foundational problems. It's happening again next March in Anaheim. So if anybody are interested, I think it has been fun. I think a number of people in this group actually also was invited to give invited talks at various years. And that's one main reason actually I'm going there, continuously over the last few years. Okay, and last but not least, I think what do I want to do with this group is that we certainly have things that we want to look into and hopefully can be done together with this group of people. I mean, I don't need to tell you about this. I mean, everybody's interested in the scaling. I'm interested in how attention is actually learned. I'm interested in the learning process itself, not the final result. And so like, how does it become sparser and capture a certain structure in attention? How does actually in context learning occur as sort of a dynamic persistence problem? And then finally, the generalization in transformer-based model. Can our duality relation apply here in any way? Does it lend any insight in terms of transition from memorization to generalization, like grokking? How does it happen? When does it happen? And so on. Okay, great. All right, next up. Thank you.
Right, can I ask a question about the last, this future slide?
Yeah.
There was, I may be putting too much stock in this, but there was a paper recently, let me actually put it in the plot, that was kind of like an essay type thing.
You want to share it? I mean, I'm
Yeah,
happy.
I'm sharing it. That argues that in these giant language models, which is not the be all and end all of ML, but anyway, and that in them, we're not in this regime where you're in any danger of overfitting, then instead you're in, I think what you call the transient regime, where you're, because of how much data you have versus parameters or some such thing, they argue that we have to redo the whole phase diagram of what works and what doesn't in batch size and everything. And so since yours is a non-equilibrium theory, maybe you can also, attack that problem. But anyway, I was wondering if you have comments on this, if you've seen it.
I have not seen it yet, but I think you're right. I mean, in the large language model setting, they're not even one epoch. There's no such notion of one epoch. They just keep adding on.
Right.
I think that has a lot to do with the fact that it's going downhill, or so that I think that's absolutely something that we should take a serious look at. It is that this kind of training process is not typical to the training process that we are familiar with, that we have going through hundreds of epoch.
Right, right.
So what can we get from there? Because they're in the transient region, as you said. Correct.
Right, they call it skydiving for whatever, but it's that transient.
Very fast. We call it fast learning phase. I think
right.
Very correctly.
I had another question. This may be too much for a free association, but you have this map between X and weights W.
Right.
Is that a way to think about in context learning where you compare what you would have gotten if you trained differently, changing the weights versus if you change the prompt, so to speak, which is like changing X?
Yeah, I think there might be something to do. I don't know. I mean, effectively, you're probably doing something like that because the pre-trained model, you are not doing anything to the weight, right?
Right.
Maybe effectively I don't know. I mean, this is something that very, I have no idea. I mean, but this is just an interesting phenomena to me. And I think
if you do have this map, it sounds like it, at least in word calculus, it sounds like you could relate the two things.
Yeah, I should definitely think more about it. I'm sorry.
No. Thanks a lot for the talk. Very interesting.
Okay.
Yeah, go ahead, Paul.
Just a quick reference question. Bernd sent a link to his paper, which refers back to inverse flatness, variance flatness relation in PNAS. But I'm curious about your second half, where you talked about the generalization and using the training data and a change in weights to simulate what the test data would tell you. Is that written up?
Yeah, that's published also that's last year. That's a paper. Hold on. Let me reshare again. Oh. Yeah, that's a yeah, I try to I mean again, don't make me wrong. I do have a lot of other people's work in mind when I think about this, but yeah, I have no time to quote their work, right? So forgive me if I forget about other people's work. So that's just purely for the purpose of try to go a little bit. Yeah, so that's the paper I mentioned, Paul.
Thanks.
In a very obscure journal again. I mean, I don't publish in Europe's. That's
Yeah, I think you have the nasty habit of not submitting to archive, which makes it difficult to find these things.
We did submit to archive. It's just under a different name. This journal does to you is that they actually they force you to do all kinds of changes, including the title. So so we did submit it to archive, Paul, for both of these studies. Like my first paper in PNAS came out in 2021. Guess when it was submitted? 2018. End of 2018. Anyway, that's another thing that's that I think, okay, but so just for this audience, I talked about the APS meeting as a possible venue for this type of work, which I think I really, really encourage. This is our original intent, is to have our community, right? I'm not versed in mathematics or the language enough to publish in Europe. I take it as a badge of honor in some sense because, hey, I don't have to prove theorem, sometimes useless. I don't have to force myself to forge or to improve the accuracy by 0.001%. I just don't find that's interesting, right? So, but I think on the other hand, we do have to have a community. So I think this is great. I mean, what you guys are doing, I'm an affiliate, but I'm very full-hearted. I can do whatever I can to help, right? I'm not, in this for anything else. But on the other hand, I think this whole community does depend on having, funding situation like this, opportunity like this, as well as our own conferences that we can go to, right? And our journal, right? To publishing. So, yeah.
Yeah, I do think though that like publishing in Europe's and ICML and iClear is very useful to get the ideas out there. I do think that nobody knows about this work in the CS community, and I think it's actually really important. So for example, the CS people are proving norm-based bounds and generalization error, and they're too loose. They're talking about flatness and its connection to generalization, and they're getting units. And you seem to have a unified thing that combines flatness and norms together. So I wonder if you can come up with non-vacuous bounds or estimates of generalization error that then combines various literature and I mean, it seems like that's what you've done, but I can't quite tell how much you know
the thing is I don't prove bound. I don't know how to prove bound.
Yeah.
Sadly. But that's just, I don't care also.
But if you have a very good estimate that doesn't depend on knowing the test data.
I agree. No, I should refrain myself for saying something inflammatory. But I think, I don't publish there as my first choice, but I did have colleague and I were trying to publish there, and I provide the theory part every time, not too many times. They come up with some silly things as, hey, you're a theory guy. You're a theory paper. How come I don't see any theorem? I say, what theorem? Gosh.
Yeah, it can be annoying. I think Darshil had a question.
Yeah, I just wanted to ask a clarification question from the second part of the talk. So maybe that's related to the Benjio paper you mentioned, but when you define when you say that when you try to match when you try to transfer the change from train to test to weights, you try to match the first layer pre-activations, but that's still a stronger constraint than just having the loss being equal, right?
Yeah, it's strong. Yeah, I agree. I agree. I mean, to some later on, you can have some miraculous cancellation. Later on, you can have some residual, thing. You could.
Yeah.
But this is actually, yeah, I agree. This is actually sufficient, but with
I
this,
see.
probably not. Even within that, I have many choices of W, right? It's not just one. The choice of W I picked is a very special one. It's the one that's closest to the original weight, right? You don't have to pick that. You can by some other, you might want to pick some other things, or you layer by layer, you can absorb the differences, right?
Yeah. So what I was asking is, does that have any effect on the final result, or is that like some measure zero thing that doesn't matter?
We haven't tried that. I mean, that's just honest answer. We haven't tried. We just look at this exact relation and we just use that to make the case that, yeah, this works, and this seems to lead to these two conditions for generalization, which, as Surya was saying. So in our paper, in this paper, we did mention all the previous study on the flatness on one camp and the norm on the other camp. You agree with you. They don't talk to each other, and they fight each other, and they shoot down each other, right? So that's basically, they should be happy. There's a reconciliation.
You're the great unifier.
Thanks.
Can I ask you a question as well? It went a bit too fast for me. The generalization gap you had in terms of this sigma G and sigma W.
Right. Yeah.
So were those things that you can determine entirely from the training data? I didn't understand the answer to that question.
No. It depends on the test data. Remember,
Test data, okay.
delta X is the difference between the. So what I do is I didn't do this is also details that it's very important. What I do in come up with the final formula is I pair up the test data and the training data. I pair them up. So it depends on distribution of delta X. It depends on specific data will have different. And also this goes into not only the sigma G, it also goes into sigma W, right? So one I think criticism of our paper was that, hey, what happened to the data, right? You seem like I have a map. So the referee even said, oh, this guy is doing black magic, so it cannot be true. But I think that the one thing we need to stress, we probably didn't stress enough, is that, yeah, the data is important, but that's captured by, let's say, yeah, so for example, the CI prime, this is a data-dependent distance metric.
Mm-hmm.
This is almost equal, I mean, correlated with H of n Hessian, but not exactly the same, because there are corrections which can be big that depends on the difference between the data, training data and test data.
There was this like well-known paper that came out of Google that was trying to find good measures for generalization, and like they looked at all kinds of things like sharpness and norm.
That's the paper we cited. That's the first paper we cited.
Wait, so you're suggesting somehow we look at the product of norm and sharpness?
Exactly. That's exactly, yeah.
Has anyone actually just done that?
Well, I don't know. I mean, look, we did that, right? We did that here to show it, but you have to be careful. These are.
It sounds like you're defining a subtly different thing, because yours depends on the test data. But we could just go ahead and just systematically study trained neural networks, multiply the norm of the learned network times the sharpness. But then
you say, for example, for this distance metric, right? You say, yeah, it depends on data. But let's just say it's a constant that depends on the overall strength of the data. Let's pull it aside.
Yeah.
Right.
Interesting.
So that you're referring to that paper, Fantastic Measures of Generalization,
and
so they have open weights for all the networks, I think, and so yeah, we could just compute this product and see if we do better than the other measures, right?
Yeah, that's great.
That would be worth a very simple and nice paper, actually, if it succeeds. I mean,
yeah. So there's some details like what is HN, what is n direction? Well, how do you dot product them? Basically you do analysis. So you actually look at the principal. You look at the eigen direction, let's say for H, and you look at the variance of sigma W in that direction, and so it's not a totally just directly product. You have to project it onto different principal or eigen direction of the Hessian, let's say, as a base. right? So different, I'm saying different direction is contributing to this thing. So this is sum over n. N goes from 1 to m being the number of dimensions.
Oh, I see. I see.
But you can
Can you
certainly
introduce a cutoff?
But still, you can sum. You can just do that
sum. Yeah, just sum.
empirically, right?
So this paper, well, not that I mean, but has a lot of stuff in it. So we even break this for the simple system. We even break it up into contribution from the sharp direction and contribution from the large majority of the flat direction, right? How they compare with each other. And so different algorithm, I think, for example, if you have weight decay, the second part, because there's so many modes, so each one of them contribute even by a little amount can overwhelm the sharp direction. On the other hand, if you do SGD, what happens if you tune up the noise in SGD, the first component, the sharp direction contribution actually goes down. Right? So you can look at where does it come from, right? The contribution of the, so I think this lot more to be done. I mean, we just scratched the surface, but I think duality is the key, right? Once you have this, you can do many things. You might be able to do many things.
So Yuhai put in the links to those articles. They were up. The second one was difficult because Nature apparently forced you not only to change the title, but to add a third author.
Yes, because you know why? They want experiment on a bigger system. So we searched up and down and find this, the sort of a very, not large language model, but very large model where we applied this. That's actually the final approval was very hinged on top of that. I mean, you cannot imagine how, anyway, I don't want to go there, but that's true, yeah.
Anyway, thank you. This was great stuff.
Thank you.
Yeah.
All right. So actually, I probably need to go. So yeah, if it's okay.
Yeah, of course. Yeah. Thanks so much. And to everyone, it'd be really great to restart this in January again with lots of talks. I'll reach out about that.
Okay.
Okay. Thanks a lot.
All right. Thank you. Thank you. I'm looking forward. Yeah.
Bye. Thank you.
Bye, everyone.